Back in chapter 7, we looked at chemical reactions. We looked especially at how to describe them, how to categorize them, and so on. In this chapter, we're going to go into more detail. We're going to look at how reactions work. Basically, we're going to look at kinetics, that's factors affecting the rates of reactions, and how we can control that. And then we're going to look at a special class of reactions called reversible reactions. In reversible reactions, we can set up what's known as an equilibrium, and we'll go into more detail on that. So first of all, let's talk about how reactions themselves work. One way to understand reactions is through what's called collision theory. All right, so basically, collision theory states that reactions happen because reactant molecules collide in a particular way. And these collisions, or controlling these collisions, affects different aspects of the reaction. So basically, you need to meet two requirements for a successful collision. All right, so first of all, the molecules have to collide in the right orientation. They have to hit each other the right way. Secondly, they have to hit each other hard enough. If they are not going to collide with enough energy, they just sort of bounce off each other. Okay, so those are the two requirements you need to have a successful collision. So in this example down here, we have a nitrogen molecule and an oxygen molecule, and they have to hit each other sideways, as shown, with enough energy to make two nitrogen monoxide products. Okay, and that's what we mean by a successful collision. So you can see here that if they don't hit each other hard enough, they hit each other with insufficient energy, they just kind of bounce off each other and remain the same reactants. All right. Likewise, if they don't hit each other in the same sideways orientation that we saw in the previous slide, if they hit each other head on, or one of them hits head on while the other one's sideways, you can see again that does not have the right setup for a successful collision, and we don't get the product. We just wind up with the same reactant molecules. They just bounce off each other. Now you're probably saying to yourself, wait a minute, it looks like it's really difficult to get a successful collision. How do reactions even happen if it's so hard for a collision to be successful? Well, the thing you have to remember is that when it comes to molecules, they're really, really tiny, which means we have lots and lots and lots of them in a given sample, which means that there are lots and lots and lots of collisions. So even though there are a lot of unsuccessful collisions, there are still sufficient successful ones to have the reaction happen in a reasonable amount of time. Okay, so let's look a little bit more into more detail into what governs that rate of reaction, the speed of a reaction happening. Now, one of the things we've got to look at is what's known as activation energy. This is tied in to that necessary energy for a successful collision. Okay, so we've actually seen activation energy way back in chapter 8 when we looked at the energy tied into reactions. When we looked at exothermic and endothermic reactions, I pointed out there was a bump in our reaction coordinate diagram, and I explained or I mentioned that I would explain it in a later chapter. Well, this is that chapter. Basically, activation energy is that necessary energy to break the bonds in your reactant to allow the pieces, those atoms, to form the products. Okay, so if you do not have your atoms collide with that necessary activation energy, your molecules your reactant molecules just bounce off each other and remain reactants. They do not go on to form products. Okay, so that's how the activation energy is represented there. It's kind of a bump in that energy diagram because you have to reach a particularly high energy that's sufficient to break those bonds. Okay. Yeah, so even in the case of exothermic reactions, where your products are going to be at a lower energy than your reactants, you still have to overcome an activation energy barrier. Okay, a good example of this is with any combustion reaction. Combustion reactions are always exothermic. basically anything that's flammable wants to be carbon dioxide and water vapor from an energy standpoint, right? They're more stable in that form. So why doesn't gasoline just spontaneously ignite? Well, you need a spark to set off that reaction. That spark provides the activation energy. The rest comes from the exothermic nature of the reaction. Okay, anyway, I'm going off on a tangent here. The bottom line, the key takeaway from this is that activation energy is that sort of energy barrier that you have to overcome to have a successful collision. Okay, so we're going to measure the speed of a reaction typically by looking at the amount of product generated per unit time. How much product do we make in a given amount of time, let's say per second or per minute? Okay. You can also measure the reaction rate by looking at the speed at which a reactant is used up. That's also another common way to do it. Now, what affects the rate of a reaction? Well, we're going to see that things like temperature affect this, concentration. We're going to see the effect of a catalyst, for example, on a reaction. All of these are ways to influence the rate of a reaction. Okay, the temperature one's probably the easiest one to recognize, just having talked about activation energy. If you think back to kinetic molecular theory, think back to our chapter on gases, and when we talked about how the average kinetic energy of your molecules is related to temperature, right? If the temperature increases, that tells us that you're raising the average kinetic energy of your molecules. Well, if your molecules are moving faster, they have more kinetic energy, they are probably going to hit each other harder when they have a collision, and therefore they'll have more successful collisions. Okay. Concentration is another way to influence the rate of a reaction. Okay, so generally, if you increase the concentration of your reactants, you increase the probability of having a collision, and therefore you're just going to have more successful collisions along with that. Okay, so for example, if we double the concentration of one of our two reactants in this example here, so if we double our blue reactant, we double the odds of a collision, and therefore the rate will double. Okay. Likewise, if we double both our concentrations, our red and our blue reactants, we actually wind up quadrupling our reaction rate. There's 4 times as many potential collisions that we've allowed for now. Okay. For those of you going on to Chem 111, 112, it's a little bit more complicated than this. If you go into those classes, you'll learn a little bit more about rate orders for reactions, and you can see that this is a little bit more nuanced than the way I'm describing it here. But for now, this is the key takeaway you can get from this. Generally speaking, if you increase the concentration of a reactant, it will increase the rate of the reaction in general. Okay, so I mentioned a catalyst earlier. Now, what is a catalyst? A catalyst is any substance that speeds up a reaction without getting used up by the reaction itself. So it's not a reactant itself. When you finish the reaction, your catalyst is still left over. Okay, but the catalyst it is involved in your mechanism for the reaction, and by having it present, it causes the reaction to go through an alternative mechanism that has a lower activation energy. Now, we've seen that the activation energy is a barrier to a successful collision, right? The higher your activation energy barrier, the harder your molecules have to hit each other in order to have a successful collision. So if you have a lower activation energy, you're going to have more successful collisions, and therefore the rate of reaction will increase. Okay, so that's basically what a catalyst does. It just lowers the activation energy by providing an alternative mechanism for the reaction. All right, so those are 3 ways to influence the rate of a reaction. You can increase your concentration of your reactants. That'll typically give you more collisions and therefore more successful collisions. You increase the temperature. Your molecules now are going to have more successful collisions because they have more kinetic energy to meet that activation energy barrier. And adding a catalyst, of course, lowers the activation energy barrier, so more molecules can have more successful collisions. So here's a quick learning check. Take a second, pause this video and ask if each of these steps will increase, decrease, or not have any effect on the rate of a reaction. Okay, so here are the answers. All right, so you can see that for each of these basically either increases or decreases the rate of the reaction. None of these really are neutral, so to speak. Okay, so you can see that generally increasing your temperature will increase your rate of reaction because your molecules are moving faster. They're going to hit each other harder, have more successful collisions. If you remove one of your reactants, I think here they're implying you're removing some of it. You're not removing all of it. Obviously, if you completely remove a reactant, you're not going to have any reaction, right? Because you have a reactant missing. But I think here, by remove one of the reactants, they mean you're lowering the concentration. So there's going to be fewer of those molecules available to have collisions, and therefore there's going to be fewer successful collisions. Adding a catalyst, of course, we see that increases the rate. Placing the reaction flask on ice, that's just another way of saying that they're decreasing the temperature. Okay, so it's the opposite of A. And then, of course, increasing the concentration of a reactant is kind of the opposite of B. That's why that increases the rate. All right, here's another way of putting a question in that form. Here we're using a specific example. Here we have carbon monoxide reacting with oxygen to make carbon dioxide. Okay, so in a similar way, look at each of these steps we've taken in A, B, C, and D, and ask yourself for each of them, will they increase or decrease or not have an effect on the rate of this reaction? Okay, so pause this video and come up with an answer for each of these. Okay, and so if you're back, here are the answers. So, if basically if you raise the temperature, again the reaction will speed up because you have more kinetic energy for your molecules. They're going to have more successful collisions. Removing oxygen, again, here it's not removing all the oxygen, just removing some of it, lowering its concentration. Adding a catalyst, we've already seen that just automatically will increase your rate. And lowering the temperature, basically, again, that it's the opposite of A there, so you're going to have the opposite effect. Oh, a quick note here about adding a catalyst, especially in a situation here like where they give you the equation. If you ever see an equation written out telling you what's going on, remember, a catalyst is not a reactant or a product. It will not be written on either side of that arrow. Instead, if your equation does describe the use of a catalyst, you'll see the catalyst written over the arrow. So, for example, back in the lab that where we looked at types of reactions. If you recall, we did a decomposition of hydrogen peroxide, and we catalyzed that with potassium iodide. So if you recall, there was Ki written over the arrow. Okay, of course, Ki standing for potassium iodide. So that's typically how you will show that a catalyst is present when you have an equation written out. Here they left it out because they were just giving the generic equation, but if you had a specific example, that's what they would do. Okay, so that brings us to reversible reactions. Now, reversible reactions are interesting. You haven't seen this situation yet, but basically, up until now, you've kind of just treated all reactions as just happening in one direction. Your reactants make your products, and when your products are made, that's what they are. They just stay products. However, it is possible to have two reactions sort of coupled together, where you have your reactants forming products, but at the same time, those products can undergo a reaction where they go back to forming the original reactants. Okay, we call that a reverse reaction. And so coupled together, if you have a forward reaction and a reverse reaction, the two combined are known as a reversible reaction. All right, so for example, here we have a synthesis reaction where sulfur dioxide reacts with oxygen to make sulfur trioxide. Okay, so that's your synthesis reaction where you're taking multiple reactants to form one product. Now, sulfur trioxide can undergo a decomposition reaction where it will decompose into sulfur dioxide and oxygen. And it turns out that both these reactions happen at the same time. So you can set up a system where you have sulfur dioxide and oxygen forming sulfur trioxide, and at the same time you have sulfur trioxide decomposing back into sulfur dioxide and oxygen. Okay, so now to show this, to show that both reactions are happening at the same time, we often have a double arrow like this. Now, this is done on a PowerPoint slide and it's written with two actual double-headed arrows. Typically, when people write this by hand, they use an equilibrium arrow that looks like this. So typically, you'll see two single-barbed arrows pointing in opposite directions. All right, so that's what an equilibrium arrow looks like. So, what is equilibrium? Well, if you have these two reactions going on in a reversible reaction, a forward reaction and a reverse reaction, they have their own rates of reaction, right? We've seen all the factors that that influence the rate of a reaction, right? Well, you have these individual rates. However, think about what's happening to your reactants and products for each of your reactions. Your reactants for your forward reaction are the products of the reverse reaction and vice versa. So as your forward reaction picks up, you start using up those reactants. Conversely, you start adding up, you're increasing the concentration of the products, which remember are the reactants for that reverse reaction. Okay, so basically your forward reaction is going to slow down as you use up those reactants. Your reverse reaction is going to speed up as you increase the amount of product. So eventually you're going to reach a point where both rates are equal. You're going to make product as quickly as you use it up. So now if you're observing this system, it's going to look like the system's static, like the reaction stopped. Technically it isn't. It hasn't stopped. This is what we call a dynamic equilibrium, where the forward rate and the reverse rate are equal. Okay, and that's why appearance that the reaction stopped is just an illusion. The reaction's still going on. It's just that, the two rates kind of seem to cancel each other out. Now, very, very important point here that I think a lot of students mess up on. Just because you've reached a system at equilibrium, that does not mean you have the same amounts of reactants and products. Okay, it means the rates are equal. It does not mean that the concentrations of the chemicals are equal. It is possible to have a lot of reactant and very little product at equilibrium, or vice versa. You might have a lot of product and very little reactant. We'll talk a little bit more about this and look at how we quantify this later on in this chapter. But for now, I just want to make that distinction that the concentration of your reactants and products do not have to be equal at equilibrium. What equilibrium means is that those concentrations stay constant. They don't change once you've hit equilibrium. Okay, let's look at a specific example here. So let's say we have an equilibrium between hydrogen, iodine, and hydrogen iodide. So our forward reaction has hydrogen and iodine undergoing a synthesis reaction to make hydrogen iodide. Simultaneously, our hydrogen iodide is going to decompose back into hydrogen and iodine. Now, let's look at a system as it approaches equilibrium and once it hits equilibrium. So let's say we started off with a sample of hydrogen and iodine only. Okay, so if we look at our circle on the left, this is our reaction mixture. Notice that we have these white molecules representing hydrogen, these purple molecules representing iodine, and those are the only molecules present in our sample. So think about the rates of your reactions. That forward reaction is going to have a pretty high rate because you've got a lot of your reactants. Those concentrations of hydrogen and iodine are pretty high. So you're going to have a really fast rate for that forward reaction. Now, think about the reverse reaction. In the reverse reaction, hydrogen iodide is going to decompose into iodine and hydrogen. There's no hydrogen iodide in this sample. So the reverse rate right now is 0. There's no reactant, so to speak, for that reverse reaction. Now, let's give a little bit of time here. So this reaction, the forward reaction happens, and we start making hydrogen iodide, represented by these purple and white molecules here. Okay, now notice we only a little bit of time has passed. We've made a little bit of hydrogen iodide, so it's still a very low concentration there. We still have a lot of hydrogen and iodine present in our sample. So notice that our forward rate is still pretty high. It's decreased a little bit, but it's still a pretty high rate. But notice also that our reverse rate is starting to pick up. Okay, it's very low though right now because we don't have a lot of hydrogen iodide. Let's go forward in time a little bit more. Now, again, because that forward rate is still fast, you're going to start making more and more hydrogen iodide molecules, as you can see here. So that means that that reverse rate is going to keep on picking up. But to do that, you're using up hydrogen and iodine. And notice we have fewer of those molecules floating around here. So that forward rate is going to decrease. Okay, so you can see where this is going, right? Once we've hit equilibrium, these two rates are equal. Okay, so it doesn't matter now where in time you go forward. You can basically you can sit there watching it for a very, very long time. You can see here the time lapse here is like 21 hours later. It's still the same, right? Those rates are still even. Okay, that forward and reverse rate are going to equal each other out. Now, please note though that we do not have equal amounts of hydrogen iodide and our reactants, hydrogen and iodine. Notice in this sort of sample, we have only one hydrogen molecule and one iodine molecule, and we have 6 hydrogen iodides. Okay, and same here 24 hours later. Okay, now please note, of course, that this hydrogen molecule is not the same as this hydrogen molecule here. Same with this iodine and this iodine. Basically, it's not like the reaction stopped. It's just that the rates are equal. So you're getting, some of these hydrogen iodide molecules are being converted into hydrogen and iodine. It's just that simultaneously that hydrogen and iodine is forming more hydrogen iodide molecules. Okay, so that rate seems to it seems to cancel each other out. Okay, let's practice some of these concepts. So here's an example of a reversible reaction, okay, as evidenced by this reversible arrow over here. So see if you can split this into the forward and reverse reactions. Okay, so again, pause this if you want to take some time to write this out. But the forward reaction should hopefully be pretty straightforward because this is already written out in the order that we need to see it. We've got our reactants on the left-hand side. We have our products on the right-hand side. So as we've defined this reversible reaction, this is our forward reaction. We just need a regular arrow here to show that. Okay, as seen here. To get the reverse reaction, you just flip your reactants and products. What are the products in your forward reaction become the reactants in your reverse reaction. And vice versa. Your reactants in your forward reaction are the products in your reverse reaction. You could think of it as kind of following that arrow that's pointing backwards. It's as if you've just written this equation backwards is all. Okay, so we have our systems in equilibrium when we have this forward and reverse rate equal each other. Okay, and that's great. But we want to try and understand these systems in equilibrium a little bit better. How can we describe them? And then how can we manipulate them? How can we make them do things that we want them to do? This will involve understanding how they respond when we do things to kind of mess them up. We'll get into that a little bit later on in this chapter. Let's start off by defining or describing these equilibria. Okay, to do that, we're going to write out what's called an equilibrium constant, or equilibrium expression. And to do this, we're going to use an equilibrium constant that we write out with a capital K. All right. It's often written as Kc. The C just tells you that we're dealing with concentration here. In this class, we're mostly going to be dealing with Kc for these equilibrium expressions. you can get other forms. For example, with a gas, you could have Kp, where you use the pressure of gases and so on. But for now, we'll just assume that most of these are going to be Kc expressions. Now, how do we write out concentration? Well, in chemistry, we prefer to use concentrations in molarity, right? Very, very useful for chemists because we're dealing with moles there in a particular volume. Now, the shorthand for molarity is to use these square brackets, okay? So we use these square brackets to say that we're talking about the molarity of whichever chemical. So when we write out our equilibrium expression, we put down the concentration of our products over the concentration of our reactants. Okay, we have that ratio of products to reactants in our equilibrium expression. Now, so for this generic equilibrium here, where we have chemical A becoming chemical B, the concentration of chemical B is on the numerator of our fraction, and the concentration of chemical A is on the denominator. Now, another thing to consider when you look at your balanced equation is that the coefficients of those chemicals become the exponents in our equilibrium expression. All right, I'm using very generic terms here right now. This will make a lot more sense when we see an example in a little bit. So let's try an example out. Here we have an equilibrium where carbon monoxide and oxygen are in equilibrium with carbon dioxide. So the way this equation is written out, carbon monoxide and oxygen are our reactants, and carbon dioxide is our product. So we're going to write out our equilibrium expression. Now, again, this always has Kc, our equilibrium constant, on one side of the equation, and we're going to have that equal to our products over our reactants. So what's our product? Well, that's on the right-hand side of the equation. That's carbon dioxide. So we put CO2 in square brackets on the numerator. Okay. Please note that that 2 in front there, that coefficient, is not part of the formula of carbon dioxide. We'll take care of that in a little bit. Our reactants are carbon monoxide and oxygen. So we've got to put them on the denominator of our expression. Okay. Please note they get their individual sets of square brackets. That's because you don't have to have the same concentrations of carbon monoxide and oxygen. Okay, you could have them in different concentrations. Okay, so this is not a unified thing. You have a concentration of carbon monoxide in square brackets and a concentration of oxygen in square brackets. Okay, please note that there's no operator between these two, which means we would be multiplying these two concentrations. Okay, but almost forgot the last step. We've got to take care of those coefficients in our equation. Remember, these coefficients are going to become exponents for their respective chemical concentrations. So our carbon dioxide over here, because of that 2 written in front there, that concentration gets squared. Likewise, our concentration of carbon monoxide is going to get squared because of that 2 there. What about oxygen? Oxygen doesn't have a coefficient, which essentially means it has a coefficient of 1. So you could imagine that there's a 1 there. You don't have to write out the 1. Any number raised to an exponent of 1 is that same number. So it's kind of unnecessary to write that 1 out there. All right, and that's it. There's your equilibrium expression. So it's always in the format of Kc is equal to our products over our reactants. All right, let's practice this. Here's an equilibrium between nitrogen, chlorine, and nitrogen trichloride. So go ahead and pick which of these multiple choice answers would be the right-hand side of your equilibrium expression. So Kc is equal to what? Okay, so hopefully you guys picked answer 4 over there. So remember, we've got 2 nitrogen trichlorides, so that's going to show up on your numerator with an exponent of 2. On our denominator, we have nitrogen, okay, which has its own set of square brackets, and we have chlorine with its own set, and it's raised to the power of 3, because that's the coefficient of chlorine there. Okay, so please note that that 3 only applies to the chlorine. The exponent of nitrogen here is a 1, which of course is not written. Now, I don't know if you've noticed this, but all of the examples we've just looked at have involved equilibria with only gases, all right? Now, When it comes to gases or aqueous solutions, writing out an equilibrium expression is pretty straightforward because gases and aqueous solutions can be expressed or have concentrations expressed in terms of molarity. We've already talked about aqueous solutions. In fact, that's where we learned the term molarity in the last chapter, where we have our moles of solute divided by the volume of solvent in, or volume of solution in liters, right? Likewise, for gases, we can have the moles of our gas divided by the volume of the container it's in, right? And because gases can be compressed, this is a changeable number, all right? But what about solids and liquids? Well, solids and liquids don't have a variable concentration, so we can't, uh, basically we can't write out, we can't include them in our equilibrium expression because they just don't have a molarity. Okay, the reason for this, of course, is that they have their own fixed volume tied into their density. So basically, what do we do when we have a solid or a liquid present in our equation? How does it show up in our equilibrium expression? And the answer is it doesn't. Right? If you have a solid or a liquid present in your reaction, it does not show up in your equilibrium expression. Okay, you could consider treating it like it has a concentration of 1, and therefore you don't have to write it. Okay, so we call these heterogeneous equilibria, where it's heterogeneous because you've got multiple phases. So in this example here, we have sodium bicarbonate, baking soda, which is a solid, and it is equilibrium with sodium carbonate, carbon dioxide, and water vapor. Now, notice that the baking soda and the sodium carbonate are both solids, whereas the carbon dioxide and water are gases. So when we write out this equilibrium expression, we have our products on the numerator. So we have carbon dioxide and water. We don't write sodium carbonate because it's a solid. Our denominator would be our reactant, which is sodium bicarbonate. But since that's a solid, that does not show up. So we're dividing by 1 here, essentially, which is why we basically haven't bothered writing out the denominator. Any number divided by 1 is itself, so we just write out the numerator here. Okay. By the way, in case you're curious, if let's say there weren't any gases or aqueous solutions on the right-hand side of this equation, there were only solids and liquids. Basically, then your numerator would just be 1. Okay, you would have 1 over the concentration of your reactants. Okay, assuming your reactants are gases or aqueous. Okay. All right, so that's basically something to keep in mind. That's often a common mistake for a lot of students. A lot of students would just kind of glance at this equation and not pay attention to the state symbols and just automatically put sodium carbonate, carbon dioxide, and water on the numerator and divide it by a concentration of baking soda squared, not realizing that baking soda doesn't have a concentration because it's a solid. Okay, so watch out for that common stumbling block. So here's another learning check for you guys. Here we have potassium chlorate in equilibrium with potassium chloride and oxygen. Okay. You may, for those of you who've taken high school chemistry, you may have had a teacher who's done a demo for you using potassium chlorate. If you heat up potassium chlorate, it'll decompose and do the forward reaction. Well, it produces a lot of oxygen as a byproduct and a lot of heat as well. So if you dropped something high in sugar, like let's say a gummy bear, into a test tube where you've got this decomposing potassium chlorate, the gummy bear will ignite immediately and give off a very bright flame. It looks kind of like a rocket, or like a rocket engine giving off a flame as it's lifting off. So you may have seen this demo. If you haven't, I highly recommend YouTubing it. It looks pretty cool. All right, so hopefully you guys have figured out that the answer to this one is going to be number 4 again. Notice that potassium chlorate and potassium chloride are both solids, so they do not show up in our expression. So our Kc expression is just Kc times the concentration of oxygen raised to the power of 3, because that's the coefficient of oxygen there. Okay, so now that we've learned how to write out equilibrium expressions, we're going to learn how to use them. Okay, but that being said, if you're still struggling a little bit with that last section, I really recommend practicing writing out equilibrium expressions. We're going to look at how to deal with the numbers in equilibrium expressions, but I find that all these problems from now on out generally become a lot easier if you're comfortable with setting up the equilibrium expression in the first place. So let's look at how we can apply the numbers here. So we have an equilibrium with hydrogen and iodine forming hydrogen iodide. We can write out an equilibrium expression for this. Again, using your products over your reactants, and just as we've seen before. Now, the question tells us that the concentration of hydrogen at equilibrium is 1.2 molar. The concentration of iodine is 1.2 molar, and the concentration of hydrogen iodide is 0.35 molar. Okay. Again, please note the concentrations don't have to be the same numbers. They can be different numbers. Okay. So, what is the value of Kc? That's what the question's asking us to do. It wants us to calculate the Kc, the equilibrium constant. So in order to proceed with this problem, as I said before, you need to be comfortable writing out an equilibrium expression, as we've just seen. So we know that our equilibrium expression will be Kc is equal to our product over our reactants. Our product here is hydrogen iodide, raised to the power of 2. Our reactants are hydrogen and iodine. Okay, and just those. They have coefficients of 1 and therefore exponents of 1. Now, all we've got to do is plug in the numbers from the question. The question tells us the concentration of hydrogen iodide is 0.35. So we plug that number in here. Okay, so since we're taking the concentration of hydrogen iodide squared, we would take 0.35 squared. We would then divide that by our concentrations of hydrogen and iodine, which the question just told us are 1.2 and 1.2 respectively. So we plug those numbers in, and we take our answer and divide by 1.2 times 1.2. Okay, so if you've entered that correctly into your calculator, you should have gotten somewhere around 0.085. Okay, the question here is written in scientific notation, but again, you could have gotten this as a decimal, and that's totally okay. Just be ready to recognize the answer written in either format. But that's basically how you solve for equilibrium constants. You just plug in the number. You set up your equilibrium expression, and then just plug in the numbers from the question. Right? So the questions will pretty much always give you all but one of the numbers, and you just solve for whatever is missing. Here, let's try this one out. So here we have an equilibrium between methane and water on the reactant side, and we have carbon monoxide and hydrogen on the product side. Please note, of course, that the hydrogen there has a coefficient of 3. Okay, so first of all, write out an equilibrium expression for this equation. And then once you've done that, plug in these concentrations. You're told that your concentration of methane is 0.13 molar, water is 0.53 molar, carbon monoxide is 0.81 molar, and hydrogen is 0.28 molar. Okay, so feel free to pause the video here and figure out which of these three answers is the correct one. So hopefully you should have come up with this as your equilibrium expression, and if not, definitely correct it. So remember, your products are always go in the numerator. Okay, so our products were carbon monoxide and hydrogen, and of course, since there were the coefficient of hydrogen is 3, we put an exponent of 3 for the hydrogen. Again, that coefficient only applies to the hydrogen. The exponent for carbon monoxide here is a 1, which isn't shown. Our reactants are methane and water, so those show up on the denominator of our expression. And then we just plug in the numbers from the question here. Of course, don't forget to take 0.28 and cube that answer. Okay, please only apply that 3 to the 0.28. So I recommend doing that before you multiply by 0.81. Okay? All right, so try that out, but you should get 0.26 or somewhere in that ballpark as your answer. Okay, so that would have been A out of the multiple choice. All right, so we've seen how to solve for the value of Kc, but what does that mean, right? What does Kc tell us? The equilibrium constant gives us an impression of our system at equilibrium. It tells us what is present at equilibrium? Do we have more reactant or do we have more product? All right, let's look at an example here. Let's say we have a sample of sulfur dioxide and oxygen only. Well, they're going to eventually, they're going to make product, they're going to make sulfur trioxide, and eventually you'll have an equilibrium mixture that has all three chemicals. Now, let's say instead of starting off with those two chemicals, sulfur dioxide and oxygen, we instead started off only with sulfur trioxide. Well, in this case, the reverse reaction would pick up, and you'd make some sulfur dioxide and oxygen, and again, you'd hit equilibrium where all three chemicals are present. Okay, it doesn't matter where you start from, you're going to get about, you're going to get the same equilibrium mixture. Okay, now that's going to be interesting because in the case of this equilibrium, it turns out that at equilibrium you have a lot of sulfur trioxide, but very little sulfur dioxide and oxygen, and it doesn't matter where you start. You could have started with lots of reactant or lots of product. It doesn't matter, you're going to wind up with the same ratio of lots of product to little reactant at equilibrium. Okay, so actually, take a second here and think about this, right? What's the value of Kc going to be for this equilibrium? Okay, so if you want to pause this video, try writing out an equilibrium expression for this equilibrium. Okay, look at the concentrations here. Ask yourself, are these big numbers or small numbers? And ask yourself how that would affect the value of Kc. Okay, so hopefully if you've paused this and done that, you would have realized that your concentration of sulfur trioxide goes in the numerator of your expression, right? Products go on top, and your reactant concentrations go on the bottom, on the denominator. And you're taking a large number and you're dividing it by a small number. When you take a large number and divide it by a small number, you're going to get a large answer. And that's what happens. You get a large value for Kc. Okay, here's a different equilibrium between nitrogen, chlorine, and nitrogen chloride, trichloride, and you're told that the equilibrium expression, the constant for this expression, is 3.2 times 10 to the power of 11. That's a really large number, of course, right? It's 32 followed by 10 zeros, right? Really, really large number. What does that tell us? At equilibrium, we must have a lot of nitrogen trichloride and very little nitrogen and chlorine. Okay, quick note here. This constant is only constant as long as the temperature is constant. Okay, so it's not written here, but I'm guessing this is a value at a particular temperature. Okay, don't stress too much about that in this class. We're not going to change temperature on things, so you can assume that any problem that you do in this class that involves an equilibrium is just going to stay at that temperature. It's usually at either at room temperature or at standard temperature, which is 0 degrees Celsius or 273 Kelvin, right? But again, those of you going on to higher levels of chemistry, like Chem 111, 112, just know that this number can change if you change the temperature. Okay? All right. Anyway, the bottom line here I want you to get out of this is that whenever you have a large value of Kc, what does that tell us? It just tells us that we have a lot of product and very little reactant. We're going to get a lot of the stuff on the right of the expression and very little of the stuff on the left. Okay, then we of course can have the converse situation. What if we have an equilibrium where at equilibrium we have lots of reactant and very little product? So look at this equilibrium here between nitrogen, oxygen, and nitrogen monoxide. Okay, so nitrogen monoxide is your product, and there's very little of it at equilibrium. So ask yourself, what would the value of Kc be for this equilibrium? And you've probably figured out that for here, it's going to be a very small number, right? You're taking a very low amount of product, and you're dividing it by very large numbers for your concentration of reactant. So again, whenever you take a small number and divide by a big number, you get a pretty small decimal. Okay, so you can see here that this particular value of Kc is 2.3 times 10 to the power of negative 9. Okay, that means that decimal point is moved 9 spaces to the left. Okay, so it's 0.00000000023 is our concentration there. Okay, Oh, quick note here about units. You probably noticed that our equilibrium constants don't have any units. They're just unitless. Don't stress about units for equilibrium constants in this class. Those of you going on to Chem 111 and 112, of course, you will deal with the units of your equilibrium constants. But again, you'll see it's pretty straightforward. It's just you're just going to take the molars here, and they just kind of cancel out essentially, or you're going to have some left over, and what's left over becomes your units. Okay, but again, we're going to keep things simple in this class, so don't stress too much about units here. All right, so the key takeaway from this, of course, is that the value of Kc tells you about your system at equilibrium. If you have a large value of Kc, that means the equilibrium favors the products. You're going to have a large concentration of products relative to reactants. And vice versa, if you have a small value of Kc, okay, so we're talking about a very small decimal. So if it's written in scientific notation, the exponent's going to be negative. That tells us this equilibrium favors the reactants. So you're going to have, generally speaking, a lot of reactant compared to product. Of course, if your value of Kc is somewhere in the ballpark of 1, so I even go so far as to say it's somewhere between 0.1 and 10. Okay, so somewhere in that ballpark. That means you have roughly equal amounts of reactants and products. Okay, when I say equal, I just mean like on the same scale, right? It doesn't mean that it has to literally be equal. Okay, and so then that means that you're going to hit equilibrium with relatively even amounts of reactants and products. Okay, so here's some examples of different equilibria, and there are different equilibrium constants, and you can see how the large numbers favor the products and the very small numbers favor the reactants. You don't even have to really pay attention to the coefficients of these numbers in scientific notation. Just looking at those exponents will be enough to tell you whether, which side is favored. Okay, so here's a really quick and easy practice problem. So looking at this equilibrium here, you're told that Kc for this one is 1 times 10 to the power of 95. So does this equilibrium favor the reactants or the products? Okay, you've got a 50% chance of getting this right. But I think most of you probably realize that 1 times 10 to the power of 95, that's a really large number, right? That's 1 followed by 95 zeros. So that should tell you that this is going to be product favored, right? If you write your equilibrium expression, your HF concentration is going to be on top. So that has to be a large number for Kc to be a large number. Okay, and vice versa. Here you have an equilibrium where your Kc value is 1.8 times 10 to the negative 7. That's a very small number. So that tells you that that equilibrium favors the reactants. Okay. So let's kind of combine those two concepts that we've just covered. We've seen how to write out equilibrium expressions, right? And we've seen how to calculate our equilibrium constant by plugging in the numbers for those different concentrations. However, you can get a question that gives you the value of that equilibrium constant. If you have the value of the equilibrium constant, well, you can then solve for any missing concentrations at equilibrium. Okay, you just have to take your equilibrium expression, rearrange it for what you want, and then just plug the numbers in, like you've done before for solving for the equilibrium constant. Okay, so let's look at an example here. So we have an equilibrium between phosphorus pentachloride with phosphorus trichloride and chlorine. Okay, so even without looking at the rest of the question, you could probably assume that you're going to want to write out an equilibrium expression for this. Okay, so you can see that written here if you want to do that yourself and check your work. The question also tells you that the equilibrium constant for this equilibrium is 4.2 times 10 to the negative 2. So they're giving you the equilibrium constant. You don't have to plug the numbers in to solve for Kc. The question gives you Kc. The question also tells you that the concentration of PCl3 and chlorine is each 0.1 molar. Okay, they happen to be equal to each other. All right. What is the concentration of PCl5? So look at this equilibrium expression. They've given you Kc, they've given you PCl3, they've given you Cl2, they're asking you for PCl5. So you want to rearrange this equilibrium so that just PCl5 is by itself on one side of the equation. Now, again, please notice that PCl5 is on the denominator, so don't just send your numerator to the other side. You wouldn't get PCl5 on it by itself. You would have 1 over the concentration of PCl5. Okay, so think about, this should hopefully, from an algebra standpoint, this probably rings a bell from the way we solved for temperature in our combined gas law. Okay, so just be careful when you're solving for something on the denominator like this. Okay, but try rearranging this. So feel free to pause this video if you want to try this yourself. But if you rearrange this, you should get PCl5 is equal to our concentration of PCl3 times our concentration of chlorine divided by equilibrium constant. Okay, so if you have trouble seeing that, it might be easier to just try multiplying PCl5 up here first, and that way everything's on one line. Okay. And then, of course, you'll realize to get PCl5 by itself, you want to divide Kc to the opposite side. And that's what's going on here. All right, so when you plug those numbers in from the question, you get 0.24 molar for the concentration of PCl5. Now, a good way to check your work is to then take that answer and use those other concentrations, plug them into your original equilibrium expression, and see if you get the Kc value in the question. If you do, then you probably set this up and did this correctly. Why don't you guys try a problem yourselves? This is a very similar problem. Here we have an equilibrium between NOBr on one side and nitrogen monoxide and bromine on the other side. Okay, so go ahead and write out an equilibrium expression for this. You're told that the Kc value is 2.0, the concentration of NOBr is 0.5, and the concentration of nitrogen monoxide is 0.8 molar. Go ahead and solve for the concentration of bromine. Okay, but first step, write out an equilibrium expression for this equilibrium. Okay, so feel free to pause the video here if you want to spend a little bit more time trying this yourself. Okay, so if you've come back, you've probably written out your equilibrium expression like this. Okay, so your products are nitrogen monoxide raised to the power of 2, and bromine raised to the power of 1, which you don't have to write. On our reactant side, we have NOBr, and since there's 2 of it, we square that. Okay. Now, we want to solve for bromine, right? We want just bromine by itself, okay, just over here. So we want to move the other things to the opposite side. So to leave bromine by itself, now bromine's in the numerator, which makes this a lot easier. So we want to get rid of this denominator here. So we would multiply that up here to multiply by Kc. So NOBr squared times Kc. And we want nitrogen monoxide to the opposite side. So we're going to divide by that. So that gets divided down here. You can see we're dividing by NO squared. Okay. Again, if you're having trouble seeing how we went from here to here rearranged, I recommend breaking this down into steps like I just described. Okay. Then at that point, you just plug in numbers. You take your concentration of NOBr the question gives you, the value of Kc that the question gives you, and the concentration of NO that the question gives you. Plug those numbers in. Of course, don't forget to square your value of NOBr and square your value of NO. And that should then give you the concentration of bromine. And of course, if you want to check your work, just set up your Kc expression, plug that answer in along with the other concentrations, and see if you get the number that the question gave you for Kc. If you did, then you probably did this correctly. So that brings us to a very important concept about how we treat systems in equilibrium, and that is Le Chatelier's principle. Basically, when a system's in equilibrium, you can do things to mess it up, to take it out of equilibrium. How does the system respond to that, and how do we take advantage of that? All right, how do we get that to work for us? To understand Le Chatelier's principle, I'm going to give you an analogy here. Imagine you have someone standing on a balance board. So a balance board is basically just either a circle or a strip of wood on either a roll or a ball. And the idea is that you stand on it to try and improve your balance, right? So you've got someone standing on a balance board, they're balancing, and you give them a shove. You're mean to them, you push them to one side, so they're off balance, right? What do they do to try to get back into being balanced? So if you shift them to their right, Well, they then move all their weight to the opposite in the opposite direction. They move to their left, and that gets them back into balance. Right? Le Chatelier's principle is essentially that, but for chemical equilibria. All right. So basically, if you do something to mess up your equilibrium, the system will try to counteract it to go back to being in equilibrium. Right? The system likes being in equilibrium. It's stable that way. So if you take a system out of equilibrium, it will do the opposite of what you did to try to get back to being into equilibrium. All right? So how do we mess up a system in equilibrium? Well, we can do that in a bunch of different ways. We can change concentrations, we can change the pressure of gases, we can change temperature. All of these things will affect our equilibrium. So let's look at each of those in turn. So let's say we have a generic equilibrium here between chemicals A, B, and C. So A and B are reactants, C is a product. Okay, so just to jog your memories on how we define our equilibrium, our forward reaction takes A and B and converts it into chemical C. Our reverse reaction takes C and decomposes it into A and B. So what happens if we change the concentration of one of these chemicals? Let's say we add more of chemical A. All right, so now remember, when it comes to rates of reactions, increasing the concentration of a reactant will speed up the rate of that reaction that uses up that reactant. So if you add more of chemical A, the forward reaction, which uses up chemical A, will speed up because there's more of chemical A colliding with chemical B. All right, so as a result, your forward reaction speeds up, and you start converting chemical A and chemical B into chemical C. So what you've effectively done is you've added a reactant, but the system shifts towards the product side. It makes more products to use up that extra chemical A that you added and bring all three chemicals back into balance a little bit better. Okay, so let's look at an example using actual chemicals. So here we have an equilibrium between hydrogen and fluorine on the reactant side with hydrogen fluoride on the product side. Okay, so let's say we add more of a reactant. It doesn't matter if it's hydrogen or fluorine, anything on the left side of that equation, the system will try to use it up. That forward reaction will speed up and use up more of your reactants. Okay, and thereby decreasing removing that extra reactant that you added. Okay, it'll use up some of the other reactant as well, but the bottom line is that your equilibrium will shift towards the product side and make more products because that forward reaction speeds up. Okay, once the concentrations get back into the same ratio that they were before, now you've returned to your equilibrium. Your Kc value is the same. It stays the same again. Okay. So that's basically how Le Chatelier's principle will treat this change to the system. Now, you could also add a product. So let's look at the same equilibrium. Let's say we added some hydrogen fluoride, HF. Well, the system would try to get rid of that. Again, the system is not intelligent. It doesn't think about this. It's just that adding more HF will speed up that reverse reaction that uses up HF. And so you start getting more hydrogen and fluorine, those reactants instead, okay, because that reverse reaction picks up. Okay, and the extra HF that you added gets used up. All right. Again, not all of it. You just get back to that original ratio of the three chemicals that gives you that same value of Kc. Okay, so to summarize what we've just learned, the equilibrium will shift in the opposite direction of what you have done to change the system. So if you add reactants, the system will make products to use up those reactants. If you add product, the system will shift to the reactant side to use up those products. Okay, so the system is trying to counteract whatever you did to mess it up in the first place. Okay. All right. So, by the way, when we describe these shifts, we typically say that an equilibrium shifting towards the product side or towards the reactant side. Or sometimes you'll hear people say it shifts right or shifts left. Okay. So if something shifts right, that means it's shifting towards the product side. It means that you're making more product. Okay. So adding more reactant will shift the equilibrium to the product side, and vice versa, of course. Okay, when you say something shifts left, that means you're making more reactants. You're shifting toward the reactant side. Now, that was when you add a chemical. What happens if you remove a chemical? Let's say we removed hydrogen or fluorine, one of our reactants. Well, the system will shift to the reactant side. It will make more of that reactant to replace what you've taken. Okay, and vice versa. By the way, if you remove hydrogen fluoride, the product, the equilibrium will shift towards the product side to make more of it. Okay, again, this is just due to that imbalance you've created between those two reaction rates, and so essentially the one reaction picks up to try and bring those concentrations back into balance. Okay, and again, this is actually one of those things that we really take advantage of when we have a system in equilibrium and we want to make more of something. So, for example, if you have, let's say you're running a factory that mass produces a chemical, and you're reliant on an equilibrium to make this chemical, what you do is you run it as a flow process. You basically keep on skimming off product, and the equilibrium will keep on shifting to the product side and making more and more product. If you didn't do this, the reaction would essentially seem to stop because it would stay in that dynamic equilibrium, and you would get only a limited amount of the product that you want. You'd still have lots of your reactant left over. Okay, so this is something that we can take advantage of here. We can use Le Chatelier's principle to work for us here. Okay, so just to summarize, again, like the way to remember this is that the system counteracts what you have done to mess it up. So if you add reactants, the system shifts to the product side to get rid of it. If you remove reactants, the system shifts to the reactant side to replace it. And vice versa. If you add product, the system shifts to the reactant side to get rid of that extra product you added. If you remove products, the system shifts to the product side to make more product to replace what you've taken out. So let's practice this. Here's an example of a system in equilibrium, right? And look at each of the changes that have been made and ask yourself, which way will this equilibrium shift? Okay, so feel free to pause this video and think about, is this equilibrium going to shift to the product side on the right or the reactant side on the left? Okay, so before I show you the answers, I will point out that that second one is actually a trick question. I don't know if you've noticed this, but notice that ammonium hydrogen sulfide is a solid. And think about heterogeneous equilibrium, right? Does a solid or a liquid show up in your equilibrium expression? Okay, and the answer is no. So question B over there was a trick question. Actually, it has no change in the equilibrium. Okay, but you can see that adding our product. So here in this first question, we've added hydrogen sulfide, which is a product. So if we add a product, the system wants to shift to the reactant side because that uses up that extra product. So that's why that shifts towards the reactants. In the case of questions C and D, we're removing hydrogen sulfide or ammonia, both of which are products. So the system shifts to the product side to make more of them, to replace what you've removed. Okay, so let's look at some other ways we can affect our equilibrium and see Le Chatelier's principle in work. When you have an equilibrium of gases, or at least even if you have a heterogeneous equilibrium, but as long as gases are involved, you've got to consider that gases take up a lot of volume. Okay, that's just one of the properties of gases. Out of all the states of matter, they take up the most space, generally speaking. Right? They'll take up all the space available to them in their container. So think about how changing the volume might affect your effective concentration of gases, and therefore affect Le Chatelier's principle. Okay, so typically, if you have a decrease in volume, the system will shift to the side that has less gas. It does this to counteract your changing the volume. Because you are decreasing the volume, that puts pressure on the system. And to sort of relieve that pressure, the equilibrium will shift to the side that has fewer moles of gas, because that way, that side of the equation will take up less volume. Okay, so for example, here we have an equilibrium of nitrogen and hydrogen in equilibrium with ammonia. All right, so decreasing the volume will force this equilibrium towards the side of the equation that has fewer moles of gas, because those will take up less space. Okay, so if we look at our equation on the left-hand side, on the reactant side, we have 1 mole of nitrogen and 3 moles of hydrogen, or 4 moles of gas in total. On the right-hand side, we have 2 moles of ammonia, which is just 2 moles of gas. So the right-hand side, our products, would take up half the amount of space as the left-hand side, which has double the number of moles. All right, so decreasing the volume will shift the equilibrium to the right, because that's the side that will take up less space. Okay, so the system's trying to compensate for you decreasing the volume by trying to take up less space. And the opposite can happen here. You could increase a volume. Well, then the system will shift to the side with more gas molecules, and that will take up more space. It will make up for that increase in volume. Okay, so in this case, if you increase the volume of your container, the equilibrium would shift to the left, to the reactant side. Okay, and this is actually something that people take into account in the Haber process. That's the process by which they make ammonia. You actually wind up compressing your mixture of gases because you want to try and move this towards the product side with ammonia. So decreasing the volume would make more of that ammonia that you want. Okay, so that actually happens at one point in the Haber process. Okay, then the last thing we're going to look at is the effect of temperature on our system equilibrium. To understand this, we've got to think back to what it means for a reaction to be endothermic or exothermic. So just to jog your memories from back in chapter 7, I think it was actually chapter 8, where we talked about the energy associated with reactions. An exothermic reaction is one that produces heat. Remember, exo means outward, so exothermic means that heat is being given out or produced. So a way to think of this is to look at heat as a product in an exothermic reaction. All right, so the production of ammonia, the synthesis of ammonia, is an exothermic reaction. So you could consider heat to be a product in this reaction. Now, in the case of reversible reactions, the converse is true. So if your forward reaction is exothermic, the reverse reaction is endothermic. So you could think of, in that reverse reaction, your ammonia reacts with the same amount of heat, in this case 22 kilocalories of heat, to form nitrogen and hydrogen. Okay, so heat is a product in the forward reaction. Ammonia and heat are reactants in that reverse reaction. So we're going to treat heat like a product. So if we increase the heat, if we add heat to the system by increasing the temperature, the system would want to get rid of that extra heat. Well, the reverse reaction uses up heat. So increasing the temperature will actually shift the equilibrium to the reactant side, away from the side that has heat on it. Likewise, if you decrease the temperature, if you cool down your system, the equilibrium will shift to the right, towards the product side where heat is made up. That extra heat that's being given out will compensate for the decrease in temperature that you just enacted. Okay, so you can try to kind of treat heat as if it's a chemical. Okay, that if it helps you understand this a little bit better, and then treat it the same way we did, changing the concentration of a reactant or product. Okay. Now, this is the case where the forward reaction is an exothermic reaction. So we have heat on the right-hand side of the equation. If you have an endothermic reaction, on the other hand, heat would be a reactant for that forward reaction. So here we have the decomposition of calcium carbonate into calcium oxide and carbon dioxide. That forward reaction is an endothermic reaction. So adding heat, increasing the temperature, will shift the equilibrium to the right. Okay, because again, that gets rid of that heat. That forward reaction uses up heat. So increase the temperature will shift that equilibrium to the right to try and bring the temperature back down. And likewise, if you cool down your reaction, if you decrease the temperature, the equilibrium shifts to the left, because that reverse reaction would produce that heat, okay, and compensate for your decreasing the temperature. Okay, so if you look at our lab for lab number 12, where we look at chemical rates and or rates of chemical reactions and chemical equilibria, I think the last example we did actually involves you trying to figure out on what side of your equation is heat going to show up. Is it on the left-hand side or the right-hand side? And you take your system in equilibrium. I think it's that iron thiocyanate complex, and you put it in an ice bath and you put it in a hot water bath, and you kind of see does it get lighter or darker? Because remember, that dark red color you get is from that iron thiocyanate product that you make. Okay, so based on the change in color, you're able to figure out, whether it's making more product or using up product. All right, so just to summarize, here this table kind of just summarizes what effect your change to your equilibrium will induce in the equilibrium, right? And that's Le Chatelier's principle. So I wouldn't recommend kind of sitting down and memorizing this table. Like I said, the kind of the answer in a nutshell is that the system will try to counteract whatever you're doing. So if you add a chemical, the system will try to remove it. If you remove a chemical, the system will shift to the side that adds it, right? If you decrease a volume, the system will shift to the side that takes up less volume. If you increase the volume, the system will shift to the side that takes up more volume, right? Everything that Le Chatelier's principle does is in response to whatever change you put on the system. Okay. Same with temperature. If you remove heat by lowering the temperature, the system will shift to the side that produces heat. Okay, that gives more heat to raise the temperature back up, and vice versa. If you raise the temperature, the system will shift away from the side that has heat on it. It'll use up heat and lower the temperature that way. Okay, so I wouldn't recommend memorizing this is an endothermic reaction and here's what will happen if I raise the temperature and lower the temperature. I think that's going to waste a lot of brain space. I would try and simplify it if you can. Okay, quick note here. I like that this table includes a catalyst, and the key thing to see here is that adding a catalyst actually doesn't affect your equilibrium. It doesn't shift your equilibrium one way or the other. Remember, your catalyst speeds up a reaction rate by lowering the activation energy, right? But the thing is, it does this for your forward and your reverse reaction. So it actually doesn't affect the equilibrium. It doesn't shift the equilibrium at all. It might help you get to equilibrium faster, but it doesn't actually change where that equilibrium is. All right, so let's practice what we've learned so far with Le Chatelier's principle. Okay, so look at this equilibrium here. We've got nitrogen dioxide, and it's forming nitrogen monoxide and oxygen over there on the product side. Now, note that the reactant side has heat listed. That tells us that that forward reaction is an endothermic reaction. But you can basically treat heat as if it's a reactant. Okay, so look at each of the changes listed and ask yourself, is this going to shift our equilibrium to the left towards the reactant side or to the right towards the product side? Okay, so feel free to pause this video and I'll put up the answers in a second. Okay, so here we go. You can see that In that first question, we've added nitrogen monoxide. Now, nitrogen monoxide is a product, so the system will want to get rid, since we're adding nitrogen monoxide, the system wants to get rid of it, so it shifts to the reactant side, because that reverse reaction will use up the extra nitrogen monoxide. Likewise, if we add nitrogen dioxide, which is a reactant, the system will shift towards the product side. Lowering the temperature removes heat, so the system shifts to the reactant side to add more heat. Removing oxygen, which is a product, will shift the equilibrium towards the product side to make more oxygen to replace what you've taken. Increasing the volume. Now, when you look at the volume, look at your moles of gas. We've got 2 moles of nitrogen dioxide gas on the left-hand side of the equation. On the right-hand side, we have 2 moles of nitrogen monoxide gas, but we also have a mole of oxygen. That's 3 moles of gas in total. So if we increase the volume, right, the system wants to try and take up that extra space. So the equilibrium shifts to the right, which has 3 moles of gas. Okay, and so that's why we shift towards the product side. Okay, so the last scenario we're going to look at here is dealing with saturated solutions. Okay, now we talked about saturated solutions and soluble and insoluble salts in the last chapter, and I kind of we talked about the equilibrium involved between your undissolved solid and the dissolved solid, or rather the ions that your ionic compound dissociates into. Right? Or I guess really any strong electrolyte. Okay? When you have a saturated solution, this system is in equilibrium, right? You have some of your undissolved solid that is going to go into solution. At the same time, some of your dissolved ions are going to crash out into that solid. Okay, so it looks like the amount of solid that's settled to the bottom of your mixture isn't changing, but actually there is an exchange of solid and aqueous components going on. Okay, and that is an equilibrium. Now, one system that this happens in regularly is with insoluble salt. Now, the word insoluble there implies that we actually don't have any of our solute going into solution, right? It's staying completely undissolved. In reality, a tiny amount does dissolve. Okay, so it's just that when we say something is insoluble, what we really mean is that it's very, very, very not soluble. It's not very soluble, rather. Not that it's not soluble, it's not very soluble. Okay, so we can then describe this as an equilibrium. Okay, we can essentially describe it as an equilibrium that is very reactant favored. The equilibrium constant for this equilibrium is going to be a very small number. Right? So we call this particular type of equilibrium the solubility product expression. Right? So we have our reactant, which is just our solid on the left-hand side of the equilibrium, and on the right we have the ions it would split up into. Okay, now if we were to write an equilibrium expression for this, we'd have our products. So for here we have the example of iron 2 hydroxide, which is a quote-unquote insoluble salt. And so the parts of it that do dissolve make iron 2 plus ions, and we get 2 hydroxide ions. Okay, so remember back in the last chapter how electrolytes split up into their ions. Well, if we were to write this out as an equilibrium expression, our products would go on the numerator, so we have our Fe2 plus in one set of square brackets, and we have our hydroxide ions, which we then have to raise to the power of 2 because we get 2 hydroxide ions here. On the reactant side, which would show up on the denominator of our expression, we have iron 2 hydroxide. However, note that it is a solid, and solids and liquids do not show up in your equilibrium expression. So there is no denominator to this fraction. It's just divided by 1. Okay? Now, we give this solubility product expression a special subscript. Instead of calling it Kc, we call this Ksp, where the Sp stands for solubility product. The value of Ksp is going to be a very small number, but it will help us quantify just how insoluble our iron 2 hydroxide is. Okay, So before we get into dealing with those actual numbers, let's practice writing out KSP expressions. Okay, so let's take each of these solids, these insoluble salts, so to speak, and try writing out equilibrium expressions for them. So what I recommend first is write out the actual equilibrium. What does iron 2 sulfide split up into? Okay, and then do that for our silver carbonate here and our calcium iodate. Okay, so feel free to pause this video for a second and try this out on your own. Okay, but if you're struggling with it, I'll walk you through it. So, okay, so if you've paused this and tried this out on your own and you've rejoined us here, let's walk through how to write out the actual equilibria here. So iron 2 sulfide would be in equilibrium with its ions. So remember, all of these ionic compounds are going to split up into a cation and an anion. Your iron ion, which has a symbol Fe, is going to have a charge, a positive charge, that will help balance out the charge on your sulfide ion. Now, if iron were not a transition metal, if it were group 1 or group 2, you'd know what this charge is pretty easily. But since it's a transition metal, we need the information from the sulfide to figure it out. Sulfur is in group 16, so we know this is going to be a -2 charge, just like oxygen and other nonmetals in group 16. So the iron, because there's only one iron balancing out one of that sulfide, this must be a +2. Okay. Don't forget state symbols, of course. This is going to be aqueous, and this is also going to be aqueous. Okay, and there's our balanced equilibrium. Let's try doing this for silver carbonate. Okay, so same thing. We're going to have an equilibrium with silver ions, which are Ag+, which remember silver always has a +1 charge, right, when it forms ions. And that's aqueous, of course. Here, I'll put that aqueous sign down here so we remember. And we have carbonate. The formula of carbonate is CO3 with a -2 charge, right? That's the formula of our carbonate ion. And that, of course, is going to be aqueous too here. Now, this is not balanced. I don't know if you've noticed that. You can tell it's not balanced because this is a +1 charge and that's a 2- charge. And you can see that in the formula of silver carbonate. There are 2 silver ions for every 1 carbonate. Now remember, that 2 is not part of the formula of a silver ion. Silver is not a polyatomic ion. So that 2 should go in the front here. You get 2 free silver ions when your compound dissociates into its separate free ions. And then finally, we have calcium iodate here. So let's try that one out. Okay. So that's going to split up into calcium ions. So think about what charge a calcium ion has. Calcium's in group 2, so it's 2+. Okay, that's aqueous. And what's the formula of iodate? Iodate, as you can tell from these parentheses, is a polyatomic ion. And you actually haven't seen that before, so you probably wouldn't know what its charge is, but you can kind of figure it out. The fact that 2 of them are needed to balance out that 2+ charge in calcium should tell you what the charge is going to be, right? If calcium's 2+, the negative half of this has to be -2. But since there's 2 of these iodates, each of them must have a -1 charge. Okay, now, of course, those 2 iodate ions are no longer going to be stuck together, so that 2 is going to show up in front here. So here's our balanced equation for that dissociation. Now that we have all these equations down, okay, feel free to write out those KSP expressions. I will again point out, though, please note that your reactants are solids. Okay, so they're not going to show up in your KSP expressions. So here are the answers if you'd like to check them out. Now, please note that since we have 2 silver ions, you have to raise that concentration of silver ions to 2. Likewise, because we have 2 iodate ions, that's going to get squared here as well. Okay? And of course, please note that those exponents only apply to their individual ion. The 2 that we're squaring our silver ions by does not apply to carbonate. Carbonate's just raised to the power of 1. Likewise, this 2 over here for iodate is just for that iodate ion. It's not for the calcium ion. Calcium ion's exponent is 1, which isn't really shown here. Okay, so now that we've seen how to write out KSP expressions, it's just the same as any other equilibrium expression we've done. The only difference is that since our reactant, so to speak, is a solid, it just doesn't show up. There's no denominator to these expressions. But now that we've seen how to do that, we're going to calculate the value of KSP. Okay, so we're going to use the solubility of these salts, these ionic compounds, to determine the value of KSP. So let's try that out. So let's say we have lead 2 sulfate, which is a, again, quote-unquote insoluble salt. It has a very low solubility of 1.4 times 10 to the negative 4 molar. Okay, that's a very tiny amount of it that's dissolving. Okay, so what is the KSP value for this? Well, first of all, let's write out the KSP expression. And before we get to that, let's first write out an equilibrium. So here we have our lead 2 sulfate. It's going to split into lead 2 plus ions and sulfate ions. So it's SO4 2 minus. All right, there's one of each of these ions. It's just the formula of lead 2 sulfate, just PbSO4. Now, let's write out our KSP expression. KSP is going to equal our lead 2 plus ions concentration times the concentration of our sulfate ion. There's no coefficient for either of those chemicals, so there's no exponents for those terms. Now, let's figure out how to solve for KSP by plugging in the concentration of those respective ions. Now, how do we figure that out? How do we know what numbers to plug in here? That's where the solubility comes in. 1.4 times 10 to the negative 4 molar tells us that that's how many moles of our lead 2 sulfates dissolving in every liter of solution. So to make this simple, just assume you have a liter of solution. And note that by having this equilibrium in front of you, you can kind of treat this like a stoichiometry problem. If you have 1.4 times 10 to the negative 4 moles of this dissolved in 1 liter, how many moles of this are going to show up? Well, it's a 1-to-1 ratio, so this concentration is also going to be 1.4 times 10 to the negative 4 molar. Likewise, for sulfate, that's also a 1-to-1 ratio with our lead 2 sulfate, so its concentration is also going to be 1.4 times 10 to the negative 4 molar. Okay? So please note that it's a 1-to-1 ratio. Those numbers are going to be the same. They're not going to be halved or anything like that. Okay? So you just plug those numbers in. Our concentration of lead 2 plus is 1.4 times 10 to the negative 4. Our concentration of sulfate is 1.4 times 10 to the negative 4. So since KSP is just those two numbers multiplied together, well, let's multiply those two numbers together. And we get a KSP value of 2 times 10 to the power of 8. Okay, and that's just how you solve for KSP. Now, this gets a little bit more complicated if you have more than one of each ion. Okay, so we're going to see an example in a second now. By the way, this table here kind of illustrates just how low these KSP values are for insoluble salts. Okay, let's try an example here. We have PbF2. What's the KSP value if the solubility is 2.6 times 10 to the negative 3 molar? Okay, don't worry about the temperature. They're just telling you the temperature just because that's what the solubility value is at that particular temperature. This number would change at a different temperature, so they're just telling you the temperature just so you know it's staying constant. Okay, but the temperature itself isn't important for this problem. Okay, let's try working on this together. Again, my recommendation is you first write out an equilibrium for our lead 2 fluoride. Okay, so I will point out that PbF2 is in equilibrium, and that's a solid, by the way, is in equilibrium with its lead 2 plus ions and its fluoride ions. Okay, and that's aqueous, and that's aqueous. I know that fluoride has a -1 charge because it's in group 17. All of the halogens form -1 ions. So you can probably figure out that this isn't balanced, right? If that has a 2 plus charge and that's -1, there's a reason there's a 2 down here. But again, that 2 is not part of the formula of fluoride. Fluoride is not a polyatomic ion. So we're going to put that 2 in front here because those two fluorides aren't going to be stuck together. Okay? Okay, so based on this, hopefully you should be able to write out your KSP expression. But one thing I'm going to point out here is that if our concentration is 2.6 times 10 to the negative 3 molar, okay, so that's 2.6 times 10 to the negative 3, think about what this concentration is and what this concentration is. But note that for every lead-2 fluoride, we get one lead ion, but we get double the number of fluorides. Okay? So when it comes to calculating your KSP value, I'm going to point out that your lead ions are still going to be 2.6 times 10 to the negative 3 molar because of that 1-to-1 ratio. But for our fluoride ions, we're going to double that number. It's going to be 5.2 times 10 to the negative 3 molar. So keep that in mind when you're solving for the value of KSP. Okay, so feel free to pause this video if you want to try that calculation out yourself. Okay, but if not, well, we'll see now in a second when we write out our KSP expression. Don't forget that we have to square our concentration of fluoride because of that 2 there. Okay, so not only is it doubled because of the stoichiometry, but it's squared because of the KSP expression. So we're going to see that here. So we take our 4.2 times 10 to the negative 3, we're going to square that number. We're going to multiply it by 2.6 times 10 to the negative 3. Right, those are our two products. Please note again that lead-2 fluoride is a solid, so it does not show up in our expression. And so once we multiply all that stuff together, you should get 7 times 10 to the negative 8. Now, we can also do this problem backwards. If you are given the KSP value, you could figure out the solubility of your ionic compound. This is known as molar solubility. Okay, so we're going to keep it relatively simple here. We'll deal with examples that only have one of each ion. So quite frankly, all you really have to do is kind of just take the square root. I'll show you how this works in a second. I will point out that for those of you going into Chem 111 and 112, you will do problems that involve multiple ions. It's still set up the same way. You're still using your KSP expression. You can write out your equilibrium expression and just solve for what you need. It's just going to take a little bit more algebra to sort it out is all. Okay, but you will solve it with algebra. Okay, so anyway, as far as Chem 103 goes, we'll keep this relatively straightforward. Let's see an example here. So we have strontium carbonate, and we're told that its KSP value is 5.4 times 10 to the negative 10. Let's first write out an equilibrium expression for it. So before we do that, we have to write out the equilibrium. So strontium carbonate, right, which is SrCO3, is going to split up into strontium ions, and strontium's in group 2, so we know that has a 2+ charge. And carbonate is CO3 with a 2- charge. Okay, so if you haven't memorized the formula for your polyatomic ions, you can just look this up. Okay, and here's your equilibrium itself. So we can write out our KSP expression, where KSP is our concentration of strontium ions times our concentration of carbonate ions. Okay, now the question gives us KSP. It tells us that this number is 5.4 times 10 to the negative 10. We want to know the concentration of strontium carbonate that would dissolve. However, this is a solid that doesn't show up in your equilibrium expression. So how do we figure it out? Well, notice that your concentrations of strontium and carbonate are going to be in a 1-to-1 ratio with your strontium carbonate. In other words, if you could figure out either one of these two numbers, that would be your answer, essentially, right? Well, now the problem is you still have two things to solve for. Can we simplify this any further? Well, notice that these two are also in a 1-to-1 ratio with each other. So in other words, whatever the concentration of your strontium ions, that's also going to be your concentration of carbonate. So, in other words, these two are both the same unknown variable. So you could set that as x, or I believe I use the variable s here. So if this is s, and this is also s, because they're the same value, what's s times s? It's s squared. So if my KSP value, which is 5.4 times 10 to the negative 10, is equal to s squared, how do I figure out just the solubility value, just s by itself? How do I get rid of that squared symbol? Well, I would do the opposite of squaring something, and that is taking the square root. So the answer is just the square root of 5.4 times 10 to the negative 10. And there's your answer. So why don't you guys try a similar problem out? Here's lead 2 sulfate. The KSP value is 1.6 times 10 to the negative 8. What is the molar solubility of lead 2 sulfate? Okay, so hopefully you pause this and try this out yourself, but you quickly would realize you're just going to take the square root of 1.6 times 10 to the negative 8. Okay, it's the same setup as the other problem. Your concentration of lead ions and sulfate ions are going to be the same, so to figure out just one of them, you would take the square root of KSP. Okay, so the square root of 1.6 times 10 to the negative 8 is 1.3 times 10 to the negative 4 molar. Okay, and that's it for this chapter. So please do try, these suggested practice problems, and of course do as many problems as you like to get the hang of this stuff. I will point out that there are ways to make these problems more challenging, and I think your textbook does go into some of these more nuanced patterns. And to be honest with you, a lot of that stuff are things that we kind of skip in Chem 103. You would see them in Chem 111, 112. So just don't stress too much if you start to see a few problems that seem like beyond the scope of what we've done in Chem 103. So you'll notice that in section 11.5. So don't panic when you're reading that section. Just realize it's going into a little bit more detail than you need for Chem 103. Okay. Section 11.6 goes into the equilibria involved in acids and bases. We're going to go into a lot of that in more detail in chapter 12. So again, I've left that in the chapter of your textbook when I put your textbook together. Don't panic if it doesn't all make sense. You'll definitely recognize the setup of an equilibrium. I recommend reading it now, but also revisiting it when we go through chapter 12. All right, and as always, if you have any questions, let me know. And otherwise, thanks for your time and good luck.